like we are very much on time and moving into the final 15 minutes of this first plenary session. We discussed on several topics on detection, on how we can prevent bad things from happening, on what are the best strategies to deal with misinformation, on fake media and media forensics. I mean, well, media forensics plays a role, but there's like another side of the equation. And we want to be presenting today a competition announcement that it's gonna start very soon, and we wanted to share it with the participants today. I'm gonna be allowing my colleague Larry, Anzia, Mathis Dush, Zoe Papakipos, and Joanna Beaton to present this competition. And I hope that the public will find it pretty relevant for the topic of media forensics. Larry, the floor is yours.
Awesome. Thank you, Christian. Good to see you. Good to see everybody here today. So hopefully, I just want to check everybody can see my screen. Yeah. Good. Cool. Love that thumbs up. So hi, everyone. My name is Larry Nazia, and I'm a program manager with Facebook AI, focused on AI integrity. This is the core of the team that we have here, as you can see from the pictures and multiple faces, but there are countless others internally and externally who help kind of get this challenge and data set off the ground. You'll be hearing from myself, as well as my colleagues, Matthias, Zoe, and Joanna. And as Christian alluded to, today we are sharing that we are kicking off our image similarity challenge, as well as the data set, which officially launched today. The competition will be hosted by Driven Data, and we have the support of our co-industry supporters from Pinterest, the BBC, Getty Images iStock, and Shutterstock. So, as many of you know, the threat of misinformation and online abuse is an ever-growing problem. The area of data provenance has been getting a lot of attention lately through initiatives like Project Origin and the Content Authenticity Initiative. So as with our work in the past, if you're familiar, we've done challenges and released data sets before, whether that be Deepfake Challenge or the Hateful Memes Challenge or our ML Code Completeness Checklist. Facebook AI just truly believes that the best solutions to address many of the challenges that we face in this space come through open collaborations across the AI community. And we have a track record of this, obviously, as I alluded to the things we've done before around doing challenges, releasing data sets, and really just trying to be some of the best collaborators in this space when it comes to addressing these online challenges that affect social media platforms. So the next phase of this launch or this effort is our image similarity data set called DISC21, as well as the image similarity challenge with which both launched today. So, like I've said before, like deepfakes and hateful memes, other adversarial challenges out there, manipulated content will continue to evolve. And we believe that by providing this first of its kind data set, kind of expressly made to help researchers tackle this problem, along with kind of providing a common benchmark and a common benchmark data set, as well as this community competition, we're confident that the image similarity challenge will spur kind of faster progress across the industry in dealing with harmful content and really help advance the similarity detection domain. So our challenge consists of 2 tracks, and Matthias, my colleague Matthias, will kind of go in detail around what these 2 tracks are about. But the big kicker here is that we're offering a total of 200,000 in prizes, 100K each for each track. All right. So please sign up, check it out, share it with your friends, all that stuff. So our motivation for this, right, it's probably fairly obvious. As I first stated previously, image manipulation can, really lead to some of the most highly viral kind of fun moments, but also moments that aren't so great, right? Not always benign, so to speak, right? If we think back to moments like the Christchurch terror attack or the Capitol Hill incident in the US with the COVID misinfo doctors, a lot of times, yes, the viral moment is a problem, but it's really addressing these issues at scale too. Like a lot of times we know it's bad, we can find it, we can take it down in content moderation, but users who reshare, repost also creates a problem of virality when these instances get reshared. A lot of times it's benign. They're just trying to share information, but at the same time, they're inadvertently causing harm to online communities, right? As well as in the content moderation space, we're exposing reviewers, or reviewers are getting exposed to this content as well. So this problem alone can't be solved with content moderation. It's going to take AI tools out there as well. But in addition to like the reasons why we're doing this, as I mentioned before, the copy detection space is relatively underinvested in, from our perspective at least, and the community seems to feel sometimes if the problem is solved. So we're also releasing a paper today that kind of goes into this space in a little bit more detail. We'll kind of, I think, talk a little bit more about that at the end. And then lastly, like I said, content moderation alone cannot address these problems at scale. And, you know, these viral events really do cause harm to not just the people who have to do this content review as part of their jobs, but the people who are having to view it online. So now I'm going to pass it to my colleague Matthias, and he'll share more about the technical side of our data set and the challenge.
Okay, hello. So what are the challenges here? The first one is that copy detection systems operate at an extremely large scale, which means that on the Facebook platform alone, billions of query images are uploaded every day. And those have to be matched with the order of hundreds of millions of reference images. And so, of course, this is a systems problem because it requires a lot of compute. But the skills also constrains the operating points that we work on, because if we use typical operating points that are used in research settings, we will be flooded by false positives. The problem is handling false positives. And that's the consequence, is that the only practical setting of those systems is to operate at a very high precision, which seems to look fine, but high precision also means low recall. So that means that we are missing a lot of quite common image edits that in that setting are quite challenging to detect. And those include things like Instagram filters, or the strongest ones, mobile screenshots that include the GUI elements, or collages with different images. And so we developed a data set with the objective to model this setting, and to have a kind of model at scale of this setting of a real platform for sharing pictures. Next slide. So for this, we developed the DISC21 dataset. So the first objective of this dataset is to be open sourceable, because obviously we can't share Facebook pictures. So we built it from images from the publicly available Yahoo Flickr 100 million datasets, combined with face images from the deepfake detection challenge that Facebook ran last year. So the data set consists of 1 million reference images and 50,000 query images. Images have near duplicate matches in the references. So it's actually a tiny subset. So the task is really a needle in haystack sitting, because most of the images have no match. Next slide. So together with colleagues from the Technical University of Prague, we developed an evaluation metric that works in that setting. So the objectives being to penalize false positives and to be able to simulate a larger scale setting from this moderate scale setting. And that means that we are not going to let the participants get away with just doing a per query ranking of the results like what we do in the search engine. We require the algorithms to output pairs of tentative matches between query images and reference images, and associated confidence score with that. And then with that output, we can set some threshold, and the threshold will provide, for example, 6,000 true positives and 1,500 false positives, which translates to a precision and a recall. And by sweeping over the thresholds, we can go from a setting where we have high precision, low recall, and all the way to having almost zero precision and having the full recall. So this is shown in this precision recall plot. And what we are going to use as a performance metric to rank the users is the area under that curve, which is sometimes called the micro average precision. Okay, next slide. So as Larry mentioned, there will be two competition tracks. So the first track is just the matching track, which is an instantiation of the problem, which is you get a set of reference images and you have to return a CSV file containing the query IDs, reference IDs, and scores, and which is the set of corresponding pairs that are inferred from the dataset. Then at evaluation time, we combine that with the ground truth matches, and from this we compute the average precision. But we also have a second track, and this is the descriptor track, where we also have, the participants also get a set of reference images and query images as input. But instead of doing the matching themselves, we require them to produce descriptors for each of the images. And the descriptors are fixed size, and they are of size at most 256 dimensions. So those descriptors are entered into the evaluation, and the matching will be done on the evaluation side using just plain Euclidean distance comparison. And then this will provide the same set of matches that are evaluated using the average precision. So the reason for the second track is because it's much easier in a production setting to have global image embeddings than to have algorithms that take pairs of images and that need to do complicated operations on the pixels. And that's why we also want to favor this setting and to see how far we can get using that setting. Next slide. So the competition of rules and some elements of the timeline. So there are lots of rules, but maybe some of the most important ones are that participants should open source their code to qualify the prizes. So it's not prohibited to use closed source code, but in that case, they will be ranked but not eligible for prizes. So that's the first rule. The second rule is that query image processing and also reference images should be done independently. It's not possible to use statistical information about the other images to perform the scoring. So the timeline of the challenge runs from today, which is the kickoff, until December and the NeurIPS conference. So at the kickoff date, the reference images are released. The development query set is also released and the submission site opens. So it's open right now. And then during the months, July, August, September, and until the end of October, it's the development phase. So participants can play with the data sets, try out different algorithms, develop their things, annotate, and so on. They have the time for that. Until the end of October, where's the evaluation phase, which is very short. It runs over 2 days. So in that phase, the query images will be replaced with a final query set, and the participants have to process that to perform the matches and to submit the final results in 2 days. Then during the month of November, there will be a verification phase where we will look at the results and see if they match the code that also has to be submitted. And this will run through November until December, when the actual final results will be announced at the NeurIPS workshop. Okay, so that's for the Joanna and Zoe, who are going to actually show some images, because I think computer vision people always want to see images. So it's up to you, Joanna.
All righty. Okay, so to construct the dataset for the competition, our newly open source Ogly library was used. Ogly is a Python-based data augmentation library that supports 4 modalities: audio, images, text, and video, and has over 100 augmentations that aim to represent the most common transforms we see on the internet. During this challenge, you may actually use Ogly to augment your training data. Now, let's hear from Zoe on how Ogly was specifically used in the DISC21 dataset. Next slide.
Thanks, Joanna. Hi, so yeah, while constructing the DISC21 dataset, we used Ogly's image augmentations to automatically transform most of the 50,000 query images that we provide. The rest were manually transformed, which I'll talk about in a minute. And so we mostly applied multiple transformations in combination, since this is mostly what we see users doing on our platforms. We applied Ogly transformations to a mix of images from both YFCC and DFDC, which contain people, which are the 2 data sources we used for the data set. You can see some examples from the data set on the slide here. We used a lot of transformations that are particularly common on our platforms. For example, the screenshot example, you can see the image with the flowers has been transformed using Ogly to make it look like it was screenshotted on Facebook and reshared. Next slide, please. On some of the query images, in addition to the Ogly transformations, a deepfake technique has been applied. This technique is called CAGAN, which was developed and performed by our collaborators at Technical University of Munich. This introduces some variation in the faces for the matching images containing people, so that in this challenge, you can't really rely on facial recognition technology, for example, to match the images that contain people. Next slide, please. And so a small subset of the 50,000 queries were transformed by paid annotators, as I mentioned earlier. They were given a mix of both YFCC and DFDC images, and some examples are shown here. We find it useful to include the manually transformed images in addition to using Ogly, because people are able to perform transformations that are hard to automate, such as handwriting, drawing, highlighting, or combining just the salient parts of images, which you can see in these 4 examples. And these types of transformations are very common on our platform, so we wanted to make sure to include them in the DISC21 dataset. And now I'll pass it back to Larry to wrap up.
Sweet, thanks, Zoe. So as I mentioned before, there's quite a few kind of resources out there. We're super excited to launch this challenging data set today. You can see links to the paper, the base code, as well as the Ogly library, as well as the 2 different competition tracks that we alluded to earlier. So definitely sign up. Feel free to shoot us questions. All the competition rules are available on the website. And I will throw it back to you, Christian.
Thank you very much.
Unless there's any questions. I don't know if we have time for that.
We are running a bit into the break time, but please, any questions, like check the links and please participate. It's important that we build the robust provenance solutions to address like the problem of misinformation in general.